Look at this picture and tell me what you see. The correct answer is twins. It is hopefully clear from this picture that these two individuals are twin sisters. However, twin sisters are only twins because there exist two of them. If I showed you a picture of just one of these women and asked what you saw, you would certainly not answer that it was a twin. You would probably describe instead a somewhat unsettling picture of an older woman who does for leopards what Cruella de Vil did for Dalmatians. Just as twins are relationally defined, so are isomers. The relationship that we play up in all isomers is that all isomers have the same formula, but are different in some other way. Most of these differences result in isomers being considered as completely different molecules with different names, with one exception. This relationship between molecules can take different forms. The simplest is just when single bonds are rotated, conformational isomers. Conformational isomers are different than all the other isomers in that no bonds must be broken for them to interconvert, and they're actually the same molecule. Atoms may be connected differently as well. For example, 2-methylpentane and 3-methylpentane have the methyls at different positions. These are called constitutional isomers. Pause and draw these two molecules to convince yourself that they have the same formula but are not the same molecule. Again, 2-methylpentane and 3-methylpentane. Isomers may also have the same connectivity, but different orientation in space. At the end of chapter 3, we saw one example of this as double bonds prevent rotation in locked groups on the two carbons, either on the same side or on opposite sides, same side being cis and opposite sides being trans. These were examples of stereoisomers. One special case of stereoisomers is where molecules are complete mirror images of each other, but are still not the same molecule. These are called enantiomers. The relationship between enantiomers is the same as the relationship between your right and left hands. This chart helps to relate some of the types of isomers, which we talk about in much more detail in the next two chapters. In this chapter, we will focus on conformational isomers and constitutional isomers, those shown in red on this chart. And we will talk in more details about stereoisomerism that actually results in different molecules in chapter 5. In order for us to understand configurational isomers, it helps for us to have good ways of visualizing configurations and how they place atoms relative to each other. This is particularly important because some molecules will only take on certain configurations because of spatial constraints, and some will react very differently in different configurations. A Newman projection is a way that we typically think about the relationship between atoms attached to adjacent atoms. The nearest atom, typically a carbon, will be depicted as a point. Substituents will space themselves around the atom equally, and their bonds will come together and meet at the point, making a Y shape for tetrahedral atoms. The bond that we are looking at is behind the first atom, so we draw the second atom as a circle, again with its substituents spacing equally around it. These substituents have their bonds marked only to the edge of the circle. The Y shape for the front atom and the Y shape for the back atom can be rotated relative to one another to represent all the possible orientations around a single bond, with the orientation being shown having the lowest energy, because all the bonds are staggered relative to each other. Again, these Newman projections allow us to represent all the orientations around a sigma bond. However, this is most interesting every 60 degrees as we rotate between having the groups on the front and back completely staggered to completely eclipsed, and vice versa every 60 degrees. You can see ball and stick models of this with matching Newman projections right here. Notice that even when we mean to indicate groups on the front and back atoms completely in line or eclipsed, we draw them slightly off from each other so we aren't writing atoms on top of each other. The previous slides showed the rotations in 60-degree increments amounting to a half turn, and this slide simply shows the other half turn, again alternating between the highest energy, the eclipsed conformations where everything's in line, and the lowest energy where everything's staggered. I've mentioned a few times now that staggered configurations are lower in energy than the eclipsed conformations. This is because staggered interactions keep the bonding sigma orbitals as far apart as possible, while the eclipsed configurations lead to a significant overlap between filled orbitals. You might be remembering back to chapter 3 and thinking, I thought orbital overlap was a good thing and led to bonding interactions. That's a good thought, but remember, bonding interactions occur when filled and empty or two partially filled orbitals interact. Filled orbitals already contain negatively charged electrons at capacity and only repel one another. The strain between head-on repelling of orbitals is called torsional strain. Let's take those 60-degree rotations and plot the energy of each of them. The eclipse conformations are much higher in energy, and the staggered are at a minimum. The difference in energy is about 3 kilocalories per mole, or 1 kilocalorie per mole for each set of eclipsing hydrogens. Write that down. An eclipsed hydrogen-hydrogen costs about 1 kilocalorie per mole every time it occurs. The 3 kilocal per mole total difference in energy is called the rotational energy barrier. This barrier means only molecules with sufficient energy have, quote, free, unquote, rotation. This is not large, but at room temperature, only about 2% of ethanes have this energy. Before you lament the plight of the many, remember that any individual atom is just one collision away from having sufficient energy, and these collisions are constantly happening. If an ethane can't rotate now, it will be able to soon. The interactions between hydrogen in a staggered position is negligible, and the interaction even in eclipsed positions is relatively minimal. However, we could have all sorts of atoms besides hydrogens. Take, for example, this 1,2-dibromoethane. The bromines are now large enough that they will have interactions even when they are staggered but adjacent. The strain from the size of the bromines is called steric strain. Notice that if we plot the relative energies of 1,2-dibromoethane as it is rotated, the curve has a more complex shape. The lowest energy configurations are still the staggered ones, but the configuration with bromines anti or opposite one another is more stable than the configurations with bromines next to each other, which we call gauche. Similarly, the highest energy is when the bromines are on the same side, which you can see at the top. It's cis, where the other eclipse configurations that match bromines with hydrogens are far lower in energy. We can actually back calculate the cost of each of these interactions from the graph, as long as we remember that the cost of a hydrogen-hydrogen eclipse was about 1 kilocalorie per mole every time it occurred. In their plus or minus 120 degree configurations, there is one hydrogen-hydrogen eclipse interaction and there are 2 hydrogen-bromine eclipses for a total of about 6 kilocal per mole. Since hydrogen-hydrogen accounts for only 1 kilocal per mole, we know that 2 hydrogen-bromine eclipses account for the other 5. So about 2.5 kilocalories per mole each. The 60-degree structures only show gauche interactions and have a value of about 3 kilocal per mole. Write these down too. An HBr eclipse costs about 2.5 kilocal per mole, and a BR-BR gauche costs about 3 kilocal per mole. Use the same strategy to try to identify the cost of a bromine-bromine eclipse and bring your answer to class. We can have these same considerations for long chains of atoms rather than just single atoms or groups. Regardless of what the groups are, generally anti-configurations generate the least strain, so our molecules tend to be most stable in zigzag lines rather than curled back on themselves. Hence, we tend to draw our molecules in zigzag lines. Nice work, us. While this is generally true, molecules will take on other configurations some percentage of the time, and can even be forced into higher energy conformations. The molecule shown on the left entraps a 14-carbon chain and forces it into an all-Gaussian conformation. This work was done by the Julius Rebick Jr. Research Group at the Scripps Institute, which specializes in creating large molecules with special spatial constraints. They have an interesting one to bind uranium from seawater too. In this chapter, or this lesson, we've learned how to draw Newman projections and use them to assess strain. In the next lesson, we'll apply that to three-dimensional structures that include rings. In our last lesson, we talked about how molecules will take on preferred configurations, and how we can use Newman projections to visualize the relative positions of adjacent groups. This comes very strongly into play in ring molecules, where the ring often forces groups into gouged positions. Rings are really common in nature, especially 5- and 6-membered rings. We'll see why this is in this chapter. Here are a few examples that are definitely not exhaustive. Most rings have energy associated with the conformation the ring must take on. We can assess this strain by comparing the heats of combustion on a CH2 by CH2 basis. The lowest energy heat of combustion by CH2 is cyclohexane. We assume this is because it has the least strain. We can then compare every other ring to cyclohexane on a per CH2 basis to see how much strain exists. For example, the heat of combustion per CH2 for cyclopentane is 1.3 kilocalories per mole. Since there are 5 CH2 units in cyclopentane, the total ring strain is 5 times 1.3 kilocalories per mole, which is equal to 6.5 kilocalories per mole. If we compare this to some of the strain that we saw from rotation around a single bond, we realize that this is a relatively small amount of strain. However, if we look in that last column for cyclopropane or cyclobutane, we see very high energies associated with strain. Each one of our rings wants to keep its energy as low as possible and will seek to minimize all sources of bond strain. These come in 3 types. Angle strain comes from bonds not being able to adopt the angles their hybridized orbitals prefer. In an sp3 hybridized orbital, which the atoms shown all have, the bond angle should ideally be 109.5 degrees. Any other angle results in a decrease in overlap and therefore less stabilization of the bond. Geometry can give us the angles of any regular polygon, which we see don't always line up with the idealized angle. These angles assume a 2-dimensional shape, so some of the larger rings can reduce this strain by taking 3-dimensional shapes that decrease the angle. More on this soon. Torsional strain comes when bonds line up. We saw this before when groups were eclipsed. Steric strain comes from the electrons around atoms. We definitely see it in eclipsed groups, but we also see it in some gouged groups, groups that are staggered but still large enough to interact with each other. 2 slides ago, I mentioned that cyclohexane has the lowest heat of combustion per CH2 group, which indicates it has the least amount of strain. We saw last slide that cyclopentane actually has bond angles that are nearer to ideal. However, our rings rarely take on 2-dimensional structures. Look at the cyclohexane drawn with a flat structure on the left. Every one of its hydrogens are eclipsed, resulting in an enormous amount of strain. Cyclohexane reduces this strain by staggering every one of its bonds. This conformation is called the chair conformation because it looks a little like a recliner or a lawn chair. If you think about the one carbon as the feet, its carbon bonds both go up to the next 2 carbons. That's the leg rest. The next bonds to carbons go straight back, the seat. The final bonds go up to the head of the chair conformation. It may be easiest to visualize each bond straight down the bonds that make the seat of the chair, like in C. We can then draw a Newman projection that shows that cyclohexane has been able to reduce all sources of strain to essentially 0. All rings will move their carbons into a 3-dimensional structure to reduce strain if they can. Cyclopropane cannot. By definition, 3 points can only define 2 dimensions. Cyclohexane does it better than any other rings, which is why they are so common in nature. We can choose any bond of a flat cyclopentane and see that it would have the same problem cyclohexane has. Instead, cyclopentane rotates slightly around its bonds to partially stagger the hydrogens. This only occurs partially because any movement into 3 dimensions reduces the bond angle in our ring, and any reduction from 108 degrees increases the angle strain for cyclopentane. The overall conformation for cyclopentane can be visualized as looking something like an envelope that's open. 4 carbons can be considered roughly coplanar, with a fifth popped up like the open flap. Again, this conformation reduces torsional strain from eclipsed hydrogens, but at the cost of some angle strain. Overall, cyclopentane is still very low energy, and we see this very commonly in nature as well. Cyclobutane already has significant angle strain. Its angles are 90 degrees instead of 109.5, but still needs to relieve torsional strain from the eclipsing hydrogens. Cyclobutane ends up taking on a very slight pucker to reduce most of the torsional strain, but it still has a lot of angle strain. Cyclopropane would also like to relieve steric strain and angle strain. It just can't. Cyclopropane is pretty high energy compared to the other rings, and therefore most reactive. Speaking of reactivity, introducing lots of strain can make molecules way more reactive. The molecule shown is cubane, a cube of carbon alkanes. Every group is necessarily eclipsed, and there is tons of angle strain. The Navy actually funded some research on this molecule by Phil Eaton at University of Chicago. They had to put a special blast ceiling so that any explosions would blow off the ceiling rather than neighboring labs. The goal was to create a molecule so reactive that its explosion could trigger a fusion bomb. Octanitrocubane was synthesized, but fortunately enough for our world, it was unable to generate enough energy density. Because most of our rings occur in 3 dimensions, the molecules can pseudo-rotate. That is, rotate one group up and another down to flip the ring. In the structure on the left, the orange atom is pointed up, but after pseudo-rotation, any other atom can be pointed up instead. In a simple unsubstituted ring, any carbon is the same as the next then. You can trace the green atom through the rotations shown in this cyclohexane. Do that and convince yourself that they are all the same molecule. The carbons are equivalent. But now look at the hydrogen that's pointing straight up in A. Notice that it's always pointing straight up in A, B, and C, and always pointing straight down in D, E, and F. The other hydrogen is always pointing out from the ring. Unlike the carbons, the hydrogens cannot all end up in the same position. The hydrogens are not equivalent. So the carbons are all the same, but the hydrogens have 2 possible orientations. We define these 2 types of hydrogens in a cyclohexane as either being axial, pointed straight up or straight down, or equatorial, pointed out to the side. Think about this like the Earth. The axis of rotation is pointed roughly straight up and down, that's the axial, and the equator is around the middle, equatorial. However, cyclohexane can pseudo-rotate, just like cyclopentane. There are several intermediate positions between one chair and the one that has everything flipped, but after a complete flip, all the equatorial substituents end up axial, and all the axial substituents end up equatorial. Remember, this wasn't possible by rotating the molecule alone. This is a different conformation. When we pseudo-rotate a cyclohexane, we need to bring part of the molecule planar in the process of flipping configurations. This is very high energy. There are relatively stable boat-like conformations that exist alongside the chair conformations along the way, though. Notice the semi-stable conformations are twisted rather than a straight boat shape, which is higher in energy. This is because the hydrogens on either end of the boat conformation are forced into steric interactions, and the hydrogens are all eclipsed in this formation. These are relieved by twisting the boat. When the other end flips down, the molecule goes through a high energy transition state once again, and then finally becomes a flipped chair. Because chair conformations are the most common form that cyclohexanes take, and cyclohexanes are exceedingly common in nature, and the positions of substituents as axial or equatorial can affect reactivity, we really need to be able to draw our chair conformations systematically so that positioning of substituents is clear. We always draw our chairs looking from one side. The bonds that are drawn further down are considered in front, and the ones farther up are in back. Every carbon has one axial position drawn either straight up or straight down on every carbon, which you can see in the bottom, the B diagram. On any carbon, the adjacent carbons are pointed the opposite direction of the axial substituent. So you can see that carbons that are coming off of the carbon on the very left of B are both pointed up, but the hydrogen is pointed down. There is also one equatorial position on every carbon, seen in the bottom C figure, and the equatorial positions are drawn either slightly up or slightly down. The equatorials are slightly down if the axial position was up, and vice versa. Follow along on paper as we walk through drawing chair conformations. In order to draw a chair conformation, we start with two parallel lines of the same length, drawn at a slight incline down. The top line is set a little farther back than the bottom line. The left side is connected by drawing two more lines of approximately the same length as the original lines that come together as a point below and to the left. This is repeated on the right side to complete the chair. The first axial bonds can be drawn from this point on the left and the right side. Where the chair points down, the axial substituent is also down. Where the chair points up, the axial substituent is also up. They should go every other up and down around the ring. Equatorial substituents are always slanted slightly in the opposite direction of the axial position, and will again go every other around the ring. It is important to be able to draw these clearly to convey and understand information about positioning and reactivity on these rings. We go through a lot of trouble to learn how to draw cyclohexane because as soon as we put a substituent on the ring, one conformation becomes significantly more stable than the other. Even with just a methyl substituent, the axial position will have an increased steric strain with the other axial substituents on the same side, where the equatorial will not. We can see some of this strain more clearly if we draw a Newman projection that looks straight down the seat of the chair. The two adjacent sets of carbons are shown simultaneously, with the carbons connecting them shown as shared substituents between them. In the axial position, the methyl group has a clear gauche interaction with the ring itself. In addition, the hydrogens of this methyl cause steric strain against the other axial positions. Because axial positions are every other, we call this a 1,3 diaxial interaction. We're interacting with things that are two positions away. Once we flip to the opposite chair, the methyl is moved away from the ring and has no gauche and no 1,3 diaxial interactions. For this reason, it is always more stable to have a large substituent in an equatorial position if possible. This preference for equatorial positioning is moderate when the substituent is methyl, yet the methyl will be equatorial almost 95% of the time. This increases even further as we make the group bigger, which you can see from the change in preference from ethyl in line 3 to isopropyl in line 4 to tert-butyl in line 5. In biochemistry and biology, we often forgo chair conformations to talk about relative positioning. This works because the chair flips won't change the side of the molecule that a substituent is on. It only changes axial versus equatorial. We often use Haworth projections where we draw the cyclohexane laying flat to indicate this relative positioning. In a Haworth projection, the front of the molecule is drawn farther down and the back farther up, but the ring itself is drawn more or less flat. All substituents are drawn axial, so it is easy to see quickly if groups are on the same side, cis, or opposite, trans sides. Because the ring prevents groups from changing their relative positioning, cis and trans in a ring are permanent and are named just like in alkenes. Haworth projections can drastically simplify complicated molecules for viewing quickly. This is great for identification, like in the alpha-D glucose shown on the right, but it gives little information about the interactions between groups, their stability or reactivity. Cis and trans isomers of a ring can have different stabilities. For example, the cis 1,3 dimethyl cyclohexane could have both methyls on the same side and have them both equatorial. This makes the molecule much more stable since it doesn't ever need to have a substituent axial. The trans 1,3 dimethyl cyclohexane is different. No matter how it is arranged, one substituent will always be axial, and so the trans isomer is necessarily less stable. With this in mind, try to identify which is the more stable isomer of 1,4-dimethylcyclohexane, the cis or the trans. Bring this answer to class.